Welcome back to the last section of Chapter 9. In this section, we're going to be looking at modeling real-world data. We've done this throughout the year so far. This is just kind of putting it all together. And there is one type of function that we haven't really modeled yet. We haven't done much with square root functions. We just saw those at the end of Chapter 8. So we'll see that. It's done basically the same. So this is going to be mostly review, but it's nice to get all put together into one topic. So our learning targets for today: I can apply functions to problem situations, and I can use mathematical models to make predictions. So let's look at our models. This year we've gone through a lot of different models of functions. We're going to narrow it down a little bit. We're not going to use all of them. We're not going to use constant functions, not because constant functions are difficult, but because they're amazingly boring. That would just be something like y equals 3, a horizontal line. Not really worth talking about. We're also not going to use quartics or logarithmic or rational or even cube root. So the ones that we will use, we'll use linear functions, quadratic functions, cubic functions, exponential functions, and then square root functions. If we want to look at the equations of each of them, the parent function for a linear, just y equals x, quadratic, y equals x squared, cubic, y equals x cubed, exponential, it's y equals some number to the x, could be y equals 2 to the x, y equals e to the x, y equals 3 to the x, y equals 1/2 to the x. It's just a number, and that number is going to change depending on the situation. And then square root would just be y equals square root x. The graphs of them, a linear function is just a line. That's amazingly boring. Quadratic, it's a parabola. And again, these are the parent functions, so it goes through 0, 0, goes through 0, 0. The cubic goes through 0, 0 again. It's the parabola, but it's been bent downwards. The exponential does not go through 0, 0. It has an asymptote actually at y equals 0. And then the square root function starts at 0, 0 and then goes up, and it doesn't go into the negatives. So those are the graphs. When we're given points, we're given data. Sometimes, if the data is all random, we have to look at the graph. What graph does it look like it'll be? Now, if we look at a quadratic and the positive part of a cubic and even an exponential, they could all kind of look the same. And so sometimes looking at them side by side to see which one's going to be the best fit will be the most beneficial. We'll talk about that in a couple minutes. But sometimes when we're given data, we can use tables to figure out what kind of function it is. So if we had a linear function, which this is a linear function, we can check the x values, make sure they're going up by the same amount each time, which these are all adding 3. And so that's important. If these aren't going up by the same amount each time, that's when we have to graph them. Now we look at the y values, minus 2, then 5 to 3 is minus 2, 3 to 1 is minus 2, 1 to negative 1 is minus 2. And so the first difference is the same. That means this is a linear function. For quadratic, notice the x values are all going up by the same amount. They're all going up by 1. And the y values, subtract 3, subtract 1, add 3. Those are not the same, which tells us it's not linear. But now we take the second difference. We find the difference of these. So to get from negative 3 to negative 1, it's plus 2. From negative 1 to positive 1, plus 2. And from 1 to 3, plus 2. The second differences are the same, so it's quadratic. It's x squared. Cubic, remember these are going to be the third differences, so the x values are the same, and we can take the first differences, plus 2, plus 2, plus 8, and plus 20. And then the second differences, that's nothing, that's plus 0, plus 6, and plus 12. Oh, and then from what looks pretty random, all of a sudden we get plus 6 plus 6. So our third differences here are the same, which makes it cubic. Exponential's a little bit different. Our x values still have to be going up by the same amount, but now instead of adding to get from one to the next, we're going to multiply. Times 2, times 2, times 2, times 2. And that makes it exponential. It's the common ratio instead of the differences. Now, the differences should be pretty much right on, because real-world data isn't perfect. The common ratio, if these were all close to 2, it would probably be close enough. And then a square root function is a little bit different. We haven't seen these. So let's get an example of square root function. We have 0, 1, 4, 9, 16, 0, 1, 2, 3, 4. So we can take our first difference, and so plus 1, plus 1, plus 1, plus 1, that looks kind of linear. But it's not, because if we look over at the x values, these aren't going up by the same amount. It's going up plus 1, plus 3, plus 5, plus 7. Well, wait, that looks... Hey, those are all going up by 2. And so this is quadratic. But quadratic, it was the y values that did that. Or square root, it's the x values that have the same second difference. Now, why would that be? Well, let's think about what we were just looking at. We were just looking at inverses. What's the inverse of a quadratic? It's a square root. And it switches the x's and the y's. So if we switch the x's and the y's here, we'd have a quadratic. And so since they're inverses, it's the x value that's going to have the second difference instead of the y value. And then the y value will go up by the same amount, when with a quadratic, the x value would go up by the same amount. So square root is just a backwards quadratic, is really all it is. So if we have tables, we can do that. If the points aren't evenly spaced, this does not make sense, and so we'd have to graph it to see the shape. But again, sometimes a graph doesn't tell us much, and so when we do regression, we can do regression several times, kind of like we did in the polynomial chapter, where we did quadratic, cubic, and quartic, and we compared them to see which one was going to give us the best one. Just put one of them in y1, one of them in y2, one of them in y3. And so remember the regressions that we'd use for linear, we'd use linear linreg, ax plus b, quadratic's quadreg, cubic is cubic reg, exponential is the xp reg, and then square root's a little bit different. There's not one that's specifically square root, but there's one that's called PWR reg. That would be power regression. And that'll give us an equation that's y equals a times x to the b. And so this could actually work for a quadratic as long as there's no vertical shifting, no vertical translations. With a square root, it's important that we get these down to about 0, 0, so we can do a translation. If the x values or y values are really big, we can subtract everything. So if x was 3, we could subtract 3 from all the x values. And if y was 7, we could subtract 7 from all the y values. Get this, and then put those back in. Add 7 to the y values, add 3 to the x values with the equation. We don't really have to worry about that too much with what we're doing with this, but that is a possibility. Anyway, we get y equals a times x to the b. For a square root function, b is going to be about 0.5. Why would it be about 0.5? Because x to the 0.5, that would be x to the 1/2. Remember last chapter? What does a 1/2 exponent mean? It means square root. And so when b is close to 0.5, and it probably won't be exactly 0.5, it might be 0.4, it might be 0.6. That's close enough. Just make it square root of x, and you'll be good. And so we'll have a power regression as well. And so these are the deals that we're doing. I don't have an example of regressions because I don't have the right computer with me to do that. But I will make sure that we will do at least one regression in class so that you can make sure you remember how to do it. We were doing these earlier this chapter, so it's not like it's been a while, but we'll do at least one of these in class so that you'll be able to ask those questions. Until then, enjoy your evening, and I'll see you then.